showed you this experiment where we showed how if you have microwaves coming into a paraffin, that big block there was wax or paraffin, it might be reflected off the surface, but it penetrates a little bit out of the surface such that if you bring a second block close to it, it can pick up this wave that's just barely coming out and carry it through. And we got a very strong signal where the wave could tunnel or penetrate outside where it should stop and could be picked up by a second block. Now, that seems pleasant enough, and it's actually useful, but it turns out to be very applicable to a lot of things. For example, one of the very early papers trying to explain radioactivity was by George Gamow, who ended up writing some books, entertaining books on various scientific subjects. He's quite well known for those, but also did some very serious science, including the expanding universe, or the Big Bang Theory. George Gamow was involved with predicting that. But already in 1928, as soon as he heard about Schrodinger's waves, he said, well, if you have a wave inside think of a nucleus. There's some barrier holding in, say, alpha particles. They're kicking around in here. Remember we said that there'll be a wave-like pattern inside a nucleus with some barrier, but there'll be some leakage through a finite barrier, finite thickness and finite height. Well, maybe once in a while the particle can actually leak out, and we would call that radioactivity. So he was able to make a theory of radioactivity by the quantum mechanical tunneling through the finite barrier of a nucleus. You see, this nucleus is holding in the alpha particle, which is positive, but by some means or other, obviously, it's in there. But the finite barrier and the decay being finite means that there's a certain probability it will leak out. Now, here is another application of something which was achieved by Binnick and Rohrer in 1981, where they bring a metallic tip near a surface. Now, this is a drawing, actually, this is an experiment that I did myself, where we put a molecule on the surface. And we were interested in whether we could get this molecule to affect the conductivity between this tip. Now, the beauty of this artist's rendition is that it shows that there's a last atom at the bottom of the tip, which, I mean, just by sort of logic, there's going to be a last atom. It may not be quite so nice and pointy as this one, but there will be a last atom. And because the current flow is exponential, this fellow here is twice as far away, and things go down exponentially, so it's e to the 2 different, perhaps. And so the current is really very well directed through this one tip. And so you can play this tip over the molecule and onto the surface, and it's like a blind man's cane. You can actually see, if you have a small enough thing, you could see the hole, you see. But if you had a very broad tip, where am I going? There. See, if I had something like this, I could not tell there's a hole there. But if you have a single atom tip, you can see that there's a hole. So if the tip is this sharp, you can actually see things of its own general size. And so you can actually see the atomic surface of things. This is something you should know about. The scanning, tunneling microscopes, and then this spawned a whole array of fantastic developments. They have scanning thermal things, where this is a scanning thermometer. They have a thing where they measure the atomic force, namely this tip might be attracted to the surface by the atomic force, and so you don't even need conductivity. Amazing. And you can see insulating things, for example. So these guys won a Nobel Prize very soon afterwards, by the way. I'm sorry to report that Rohrer died just here. I knew him, he was a very nice guy, but he did great work. So now we have this thing. I'm not sure if in my, oh yeah, maybe this will actually work. Let me, what this is, here's a simulation of the scanning microscope. You have this tip, and here's a surface with a step in it. The idea is that you measure the current. You bring this tip within about an atom's distance of the surface, and it's so close that the wave function of the electrons in this metal tip overlap the surface such that they tunnel through. And so you get a little bit of current, and then if you move this thing, I don't know if I can move it, or it's going to do it by itself. If you move it this way, and you see that it gets closer to this step, the current will go up. And so you regulate it such that you keep the current constant. So in order to avoid that, the tip will have to rise up. Come on, let's see if you do something here. See how it moved? And it's going to jump up now because the current is too high. So if you have a device which regulates the current, it will keep the height the same. And you make a picture of the current you need to keep the current that you put into this tube to keep the current the same. I don't know if I can make that clear, but the idea is that you have this wave function. If this distance changes much, the current will change. But if you keep the current constant, you keep the height constant. And then by knowing that, you'll know the distance between the tip and the surface as a constant amount. In which case, you can see this is the surface of graphite taken in air, no less. And you can see that what's happened is the tip has gone up and down and up and down and up and down and up and down. And you just trace it across the surface. You scan, tunnel, microscope. It's quite spectacular. Very unexpected. It was one of the things where luck works out. You know, when Binnick and Rohrer did this, they didn't think they were going to get atomic resolution. It's just that there was that last atom at the bottom. They didn't count on that. They made a sharper tip that they could, but they thought they would get, maybe 50, 100 angstrom resolution. But there was that last atom, and that's what made all the difference, as the poet might say. Okay, so that's tunneling, and you see the tunneling depths are about the size of an atom, because if you put in the numbers here, the decay into the forbidden region is very rapid. How much time do we have? 10 minutes, not much. Okay, let me go over to, I wanted to, well, there's this, well, this is more tunneling stuff, actually. Here's an applet where I can have a pulse moving toward a barrier. Just for fun, let's see a step barrier with a barrier. Here's the energy of the pulse. So it's not enough to really go over the barrier, but it will reflect, but it will just show that there's a certain amount of penetration tunneling. This is more on tunneling, really. So if I let it go, you see it penetrates a little bit into here, but basically reflects back, and a little bit of penetration here. The idea of, if I change this to a barrier, you see here, even though the energy is not enough to go over the barrier, there is this wave that actually tunnels through. Now, now this is supposedly a 10 nanometer wide barrier. What do you think will happen if I make the barrier thinner? Make life easier to get through. So let me go from 10 to 5. Now you see the penetration is much greater, and the wave gets through. Now this phenomenon here is something I did want to talk about, and it's the idea that, you notice how it turns into waviness? It's because this pulse is actually a superposition of many sine waves. This is another manifestation, or is a manifestation, called the Heisenberg uncertainty principle. The fact that we have a wave confined to a certain space, namely a shape like this, means that it's composed of many sine waves. And what's happening here is these many sine waves, when they hit the wall, some of them reflect back and they interfere with the fellows that are coming the other way to give you this interference pattern that's going on upon reflection. Okay? If you go to this, you can actually have your own scanning tunneling microscope, section 1.6 of this. You can make the tip. You see, the trick is to move the tip up and down. As you get closer to the surface, the current goes up, right? Exponentially, in fact. Now, the trick is to move it sideways and keep the current constant, which is not easy to do. Now, it looks like the current is going down, and you want to come closer. This is for steady hands. You want to be able to, well, maybe I'm supposed to grab it here. Come on, guys. In any case, I should be able to scan this, and as it moves, I have to keep a constant distance above the surface in order for the current to stay constant. Okay, I'll be belaboring this too much. Let me skip over that and go to solids. Where I want, oh yeah, there's something in that I did want to talk about. Namely, let's see, this would be in the section 2.5, maybe 2.6. Okay, here's what I'm going to introduce solids here by this means. We have here something, wow, single well. Okay, we've seen this before. Namely, we have a single well, and we're trying to fit a wavy function into this well. And we show that in a confined space, not every energy gives you a standing wave. We have the condition here, that's a good one, 1/2 wavelength in the box. Okay, and then we have a second level. Notice how when I get away from that energy, the tail is really bad. It can't be normalized. But if I go up high enough energy, I find another place where there is an energy. So I have this series of energy levels in a single well. Now, let me just for fun make the well narrower, something like that. And of course, because it's narrower, I need higher energy to make its energy safe. Let me raise the barriers here a little bit more so I can get some of these in here. Okay, now, the question, to get to solids, we can do this in a sense one atom at a time. Think of this as an atom holding an electron in its lowest energy state. Granted, I can make, hopefully, what's called an eigenfunction, a characteristic function, a standing wave in the well. But you can also do this, let's put in two wells. What's going to happen is that each of the wells has its own energy states. And because of the tunneling between the wells, the state from one well will affect another. And what's going to happen is that you're going to have, in the whole story, you're going to have twice as many energy levels, which have twice as many atoms. So what that gives rise to is, here's a good state, for example, this may well be the lowest state in a double well system. But there's another energy level right nearby where, yeah, there you go. You see this one, very close by. And that is the superposition of a minus going state in this well with a plus going state in this well. But the two energy levels are close by. So one way we think of this is that this single level that was here in the single well is being split by the fact that there's another atom near it. And it's they tunnel together and they push each other apart. So the idea is then that if this were many, many, many atoms, a whole three-dimensional array of atoms, all their levels would affect each other. And this one level that started out of a single atom, or well, this one gets smeared out by the fact that by the presence of all these other atoms nearby. So this level gets smeared out. I can't get it back to an eigenlevel. Gets smeared out because of the presence of other levels. So your 1s state gets smeared into what we would call a band because of all the other atoms in the crystal. And the 2s levels get smeared out because of all the other levels, and so on and so on. And this is the origin of the band structure of solid materials. The energy levels are very close together, and they are filled with electrons just the way atoms are. So you can think of the crystal as being one giant atom. And the energy levels are like 1s-like, 2s-like, but smeared because there are many atoms whose tails basically go over to the next atom. It's an amazing picture, but it's one way of looking at things. That is, a crystal is an assembly of individual atoms, and their presence is felt by the smearing of these energy levels together. And then you do the same kinds of tricks that we did with atoms in solids. Namely, you can get light coming in and exciting, but you have a whole band here of states from which you can excite into another band. And you'll have energy gaps between bands. Or you, and you might have an empty state up here, where you can excite an electron, where the electrons fill these states, like a heavy element, but you have empty states up here. And you can knock an electron to a higher state with light or heat and so on. So this is the fundamental idea behind why there are bands in solid materials, in assemblies of atoms. You can think of them as originating in the atomic levels of the individual atoms. Now, one of the things I did want to show you while we're here, and that is the idea, while we have this demo, which I showed you earlier in class, namely the idea of why there's electrical resistance. That is to say, we know we can put an electron, a charged particle, in an electric field, and you get a force on that electric charge. And according to Newton's famous law, you'll get an acceleration, so that charge should pick up speed rapidly because there's an acceleration. On the other hand, we have Ohm's law, which says that V equals IR, and V over L is a field. And what we get is a current, which is just actually simply a constant speed of charge. So this seems like a contradiction. In one case, we would expect acceleration. In another case, we just expect a constant speed. And the answer is that this would be true in a vacuum, and this is true in a material, where the particles scatter a lot. If you have scattering of the motion, then you will get a constant speed, and that's demonstrated by this thing here, wherein, see, if I let it go here, gravity field will give it an acceleration, and it'll pick up speed. But once it starts scattering, the speed is pretty much constant. Try it again. Oh. Yeah, it's a lot different from going like this, you know, because all it is going from here to here. But there it's picking up speed all the way. Here, once it starts scattering, it's pretty much a constant speed, although there's a force of gravity. So in between crashes, it's accelerating by the force of gravity. But once it hits this, it kind of loses its speed and makes for a constant speed, not accelerated. And it's a heck of a lot slower than this. So actually, this is called the drift velocity. We've had this before. So I think we have to leave because of the colloquium. So see you Wednesday, those of you who don't want to escape for Thanksgiving too soon.